Hello everyone, how are you? I hope you are all doing well. So in today's video, we are going to study motional EMF. Okay, basically this topic comes under like the uses of Faraday's law. And in this example, we are going to see that there is a uh, there is a we can say loop MSRN in which the current is flowing. Okay. And we have introduced one conductor PQ such that it is moving towards the uh, we can say towards the side RS. Okay, with uniform velocity V. And here we can see that the direction of the magnetic field is into the phase, or we can say into the plane of the paper. Here, the magnetic field is uniform. It is not time dependent. So we are going to see that what will be the effect of that. And one important thing is here, the EMF will be induced here because of the motion of the conductor PQ that we are going to see. So we are assuming here that uh, here there will be a loop. There will always be a loop. Like the loop will be called as PQRS. Okay, PQRSP. This will be the loop at any time because the the conductor PQ will be moving towards the side RS. So at the end, it will be going to we can say it will make the rectangular loop only. Okay, so that's why. Uh, and at the we can say at the result, or we can say the as per the result of the motion of the conductor PQ, we are going to get one induced EMF. And as per if the induced EMF will be there, so obviously there will be induced current also. So we are assuming that we are, uh, let me write here. So first thing is magnetic field. The magnetic field P vector is constant, or we can say uniform, constant uniform, and it is not depending on time. Therefore, we can say that the magnetic field is time independent. First assumption. Second thing is we are assuming that there is no frictional force, or we can say the frictional force, we can say the energy loss due to frictional force is negligible. We are assuming that the surface of the we can say the loop PQRS is uh, frictionless, or we can say negligible friction, so that we are going to neglect the energy loss due to that. And we are assuming that the conductor PQ is moving with a constant speed v. Okay, it is moving with constant speed v, and here the length rs is l, and at a time t, we can say the length uh, rq is x. So as we can see that it is rectangular loop. It is a rectangular loop, so that's why its area will be, so area of the loop PQRS. Let me write here, it is a rectangle. So that's why its area will be A equals to L into X. So this will be the area of the rectangular loop. And now we are going to see that what is the direction. Okay, so the direction of the magnetic field is into the page. So now the magnetic flux will be, what will be the magnetic flux? The magnetic flux is phi b equals to b into a. So this is the magnetic flux here, and we are going to see that the magnetic field is b and the area is Lx. So equation will be here. The equation will become as BLX. So this is the magnetic flux here. Now we will apply the Faraday's law of electromagnetic induction. So according to that, what will be the induced EMF? The induced EMF will be apply Faraday's law of electromagnetic induction. Electromagnetic induction. So the EMF will be E equals to minus d phi b upon dt. This will be the EMF. Now we will place the expression for phi b and then finally we will get the expression for EMF. So EMF is minus d upon dt BLX. So from the given diagram, we can see that here what is the variable thing and what is the constant. So we can see that the length RS is length RS, or we can say the length L is constant and the magnetic field is constant. So therefore we can take them out from the differentiation. So we will get E equals to minus BL dx upon dt. This is the equation. Now, what is dx upon dt? Now we can see that at a time we can say the side rq is x, and we are differentiating it with respect to time t. So we can see that, and the conductor PQ is moving towards the length uh, rs. So therefore, the x will be going to the value of x will be going to reduce. Okay, it will going to be decreasing. Okay, so if it is decreasing, then its velocity, the value of velocity will be negative. So we can say that since since the x is decreasing with time, so dx upon dt will be minus of velocity v, because the value of velocity will be negative. So therefore, the equation will become as, okay, so the equation of the EMF will become E equals to minus of BL into minus of V, and finally we will get the equation as BL into V, where V is the velocity of the moving conductor PQ. Okay, this is the induced EMF. Induced EMF. Now, if we have find out the induced EMF, now we are assuming that, for example, let's say that the resistance of the, or we can say resistance of the conductor PQ is R. Okay, so let's say if the resistance is, if resistance is R, then the induced current what is the induced current? Induced current will be I equals to EMF upon the resistance R, and finally we will get current equals to BLV upon R. So where R is the resistance here. So this is the induced current. Okay. Now we got two equations. First is for induced EMF and the second is for induced current. Okay. So now we got two equations here. The first is for induced EMF and the second is for induced current. Now we can find out the power. Okay. So now the second thing is power. What will be the power? Power will be EI. Okay. So the equation of power will become E is BLV, and what is I here? I is BLV upon R. So the equation of the power will become as P equals to B square L square V square divided by resistance R. Okay, this will be the power loss here. Okay, now if someone wants to find out the force also, the force acting on the conductor PQ, that also we can find out. We know one another property of power, or we can say another equation of power. So let me write that. Force F. Okay, since we know that power is force time velocity. So from here we can find out force, that will be power upon its velocity v. So the force will become b square L square V square upon R into V. And finally, we will get the equation for force, that is F equals to the equation of the force is F equals to B square L square V upon resistance R. So this will be the equation of force. Okay. So that's all about the motional EMF. And now we will solve one question based on the motional EMF. How we can find out the motional EMF? Okay, let me see. The question is, so in this question, what they have given, a metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second, with one end hinged at the center and the other end at the circumference of a circle metallic ring of radius 1 meter. About an axis passing through the center and perpendicular to the plane of the ring, a constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the EMF between the center and the metallic ring? So that's we are going to find out. So first of all, let's draw the diagram. Here, first of all, let me draw the ring here, the metallic ring. So it will be, so let's say this is the metallic ring, and the radius of the metallic ring is 1 meter. And the magnetic field is constant. let's say that the radius is like since the ring, we can say the metallic rod is rotating about the center, we can say its center, and this point is P and this point is Q at a time T, and the angle is theta. And we know that here they have given the magnetic field is uniform, and it is we can say a uniform constant and uniform magnetic field of 1 Tesla parallel to the axis of the parallel to the axis present everywhere. Parallel to the axis means it will be into the phase. So that's why the magnetic field will be, we can denote it by cross signs. So magnetic direction of the magnetic field is into the phase. Like this, we can draw the magnetic field, and magnetic field is uniform, and its direction is minus k cap direction, or we can say into the phase. And now it is moving with a uniform, uniform angular, we can say angular velocity, and that velocity is omega. Okay, and the value of omega is 50 revolution per second. So omega is 50 revolution per second. Now we have to take the angle into consideration. In one revolution, there is 2 pi radians. So it will be 50 into 2 pi radian per second. So the equation will become as omega equals to 100 pi radian per second. So this is the angular frequency, or we can say the angular speed of the this rotating rod. Now the radius is given as radius is r equals to 1 meter. Okay, and the magnetic field is 1 Tesla. Okay, so now we are going to find out the EMF between center and the metallic ring. Between the center and the metallic ring means center means the point O, and the metallic ring means the circumference. So that's how we are going to find out. So for example, let's say in time t, in time t where t is greater than 0, the road like the road is rotating with speed like omega, and it traveled angular distance theta. So what will be the area of here the area of the, we can say the area of the section OPQ will be here. Now area of the section OPQ is A equals to the total area of the circle will be pi r square. And now we are going to take the fractional part like the theta upon 2 pi only, because 2 pi is the total angle due to the circle, and theta is the angle that is traveled by that road in particular time. So that's why the area will be A equals to 1 by 2 theta r square. So this will be the equation, 1 by 2 theta r square. Now we got the area also, and we have magnetic field. So now we can find out the induced EMF. Okay, so induced EMF, and first of all, uh, the magnetic flux we have to find out. The magnetic flux is magnetic magnetic flux. Magnetic flux is phi, and it is B vector dot A vector. Now we can see that we can say the road is moving in the, we can say, anti-clockwise direction. So if it is moving in the anti-clockwise direction, then its area vector will be in the we can say out of the phase direction, or we can say in the plus k cap direction. So therefore Therefore, we can write here phi b equals to magnetic field is in the direction negative k cap dot the area is in the direction positive k cap. Now the equation we will get as phi b equals to minus of BA and k cap dot k cap. K cap dot k cap is the, we can say, the k cap is the unit direction vector uh, in the z direction. So that's why dot product will be 1. So therefore we will get phi b equals to minus BA. And if we place the value, then we can say that phi b is minus value of b is 1 and the value of a depends on theta, so we can not write here. Sorry, it is not theta square, it is theta only. Half theta r square. This is the equation. Now the equation will become as phi b equals to minus 1 by 2 r square theta. Now we will apply the Faraday's law of electromagnetic induction. Faraday's law. Then we will get EMF equals to minus d phi b upon dt. Now place the values and finally we will get EMF equals to minus d by dt minus 1 by 2 r square into theta. Now we can see here that the radius is constant. It is not going to change. Only the theta is going to change. So we can further solve the equation as minus into minus will be plus and it will be 1 by 2 r square d theta upon dt. D theta upon dt is nothing but the angular velocity. So we can write here 1 by 2 r square omega. Okay. And if we would not have been placed the value of magnetic field B, that was 1 Tesla. So the equation was initially, the equation would have been E equals to half B omega r square. This is the equation of induced EMF due to the circular, we can say, where the road was moving in the, or we can say road was circulating in the circular ring. Now we will place the values, the given values. So we will get EMF equals to 1 by 2. The value of B is 1 and the value of omega is 100 pi and the value of R is 1 meter. So it's 1 square. So it was 1, right? 1 meter length. And it will be volts. Now further we will solve, then we will get 1 square is 1, 1 is 1 and 100 by 2 means 50 pi. 50 pi volts, or if we multiply then we will get uh, it is 50 into 3.14 volts, or finally we can say that it is 100 pi means 3.14 divided into 100 is 314 divided by 2, so it will be 15.7 volts. If I'm not wrong, it will be 314. Sorry, it is 157. Right. 1 second. So it will be 314 divided by 2. So the equation will become as E equals to 157 volts. So 157 volt is the answer. So that will be the induced EMF. Okay. So that will be the induced EMF between the center and the metallic ring. I hope you understood the question and the derivation both. And now if still if you have any doubt, then you can ask in the comment section.